so that on your test. I don't give busy work. Every assignment I give you has a purpose. And so anyway. Tonight, you mean?
Tonight.
If you want me to, we can just email me and we'll find a time that works for you. Okay. I can stay. I'm hoping I can stay after school today. It depends on how I'm feeling at the end of the day. Yesterday, I was not good at the end of the day. I had to get out of here. I had to go home and just sleep. And but hopefully today I'm going to feel better. So you can email me ninth period if you want, see if I'm here, or you can just stop in, see if I'm here to stay after school. Or you can just say, hey, Ms. Moso, can we do a Google Meet tonight? Okay?
Ms. Moso, on the test, will you have to do ticker tape diagrams?
Sure. They were in Unit 3. Absolutely. Okay, so let's check your study guide here. So starting with the quantities, you should know that lowercase t stands for the variable time. And it is never going to be a vector. It's always measured in the units of seconds, which we abbreviate with a lowercase s. Then D, if it's a scalar quantity, it stands for the term distance. If it's a vector quantity, it stands for the term displacement. It will always be measured in the unit of meters when we do a calculation, and that's abbreviated with a lowercase m. The variable v, if it's a scalar quantity, it stands for the term speed. If it's a vector quantity, it stands for the term velocity. They are both measured in meters per second, which we abbreviate as m over s. Lowercase a is never a scalar quantity. It stands for acceleration, which is a vector. It's always measured in meters per second or meters per second squared, which we abbreviate as m over s squared. All right, let's go through the definitions. The first one is position. The second is distance. The third is displacement. The fourth is speed. The fifth is velocity. And sixth is acceleration. Number 7 is time. All right, let's now go through the equations that you should know. They don't have to be in this order. The equations that we have when we deal with accelerated motion is the first one is V bar is D over T, which means if you were to manipulate it for D, you would get V bar T. If you were to manipulate that for time, you would get time is D over V bar. The second one is the one that you have to have memorized that was introduced and you added it to your reference table. That's the one for average speed or average velocity, which is the sum of the initial and final velocities over 2. It's like finding an average of 2 points, 2 test grades. You add them up and divide by 2. That is an equation you need to have memorized for tomorrow's test. Number 3, the third equation that we should know for acceleration is change in velocity over time, which is the same thing as VF minus VI over T. That means the change in velocity is the same thing as the acceleration times the time, or the time can be found by doing the change in velocity over the acceleration. That's VF minus VI. Number 4, VF is VI plus AT. That's right off your reference table. You should be able to move it around for all the other variables in there, VI, A, and T. Then we have VF squared is VI squared plus 2AD. You should be able to move that around for every variable in there as well. And finally, we have D is VIT plus 1/2 AT squared. Those are your 6 equations that you can use with accelerated motion. All right, let's now go to page 30. And I want to start with the column that deals with position time graphs. We're going to go down that column. So on a position time graph, the dependent variable is position. The independent variable is time. The y-intercept will give you the initial position of the object. When it's at rest, this graph will look like a horizontal line. When you're moving with a constant velocity, this graph will be a diagonal line. If you are accelerating, this graph will be a parabola. If you are moving fast, the graph will be steep. If you are moving slow, the graph will be shallow. If you are moving in the positive direction, which means to the right, the graph will go up. If you are moving in the negative direction, which in this case means to the left, you'll be going down. The graph will go down. If you're looking at the slope of the graph, you would be finding the velocity. If you're calculating an area, which we won't ask you to do, so that's why it says NA, you will not be asked anything about area for a position time graph. Then if I ask you to find the displacement, you look at the rise or the drop of the graph, the change in the y coordinates, in other words. If you're looking for the average velocity, you have to find the slope of a secant line. If you're looking for an instantaneous velocity, you look at the slope of a tangent line at that time point. And then if you're looking, well, you won't be asked to calculate an acceleration from a position time graph. Yep. Absolutely. It was part of Unit 3, right? We spent 3 class periods on secants and tangent lines. That's a lot of time. So yes, that absolutely will be there tomorrow. One of the reasons you need your ruler on the test. All right. Any questions on position time graphs? All right. Let's go to the velocity time graph then. That column. The dependent variable on a velocity time graph is the velocity. The independent variable is the time. The y-intercept will tell you the object's initial velocity. When you're at rest, this graph will be a horizontal line at a velocity equal to 0. If you're moving with a constant velocity, this graph will be a horizontal line in either quadrant 1 or quadrant 4. It's not on the velocity equal to 0 line. It's not on the x-axis. If you are accelerating, this graph will be a diagonal line. If you are moving fast, the time point is far from the horizontal axis. If you are moving slow, that line is close to the horizontal axis, close to a value of v equals 0. If you are moving in the positive direction, your graph will reside in quadrant 1. If you are moving in the negative direction, your velocity graph will be down in quadrant 4. If you're asked to find the acceleration, you would be looking at the slope of this graph. If you're asked to find the displacement, you would be calculating the area between the graph and the time axis. You can find the displacement by looking at, we said, at the area between the graph and the horizontal axis, or you could take the average velocity from your graph, which is the velocity at the middle time, or VI plus VF over 2, and multiply it by the time to give you the displacement. The average velocity on this graph can be found by either doing VI plus VF over 2 or by reading the velocity at the middle time point. So if I wanted the average velocity between 0 and 2 seconds, I would read the graph at 1 second, go up at 1 second and over, and that velocity is the average. I can get the instantaneous velocity by just reading the y coordinate at the time point that you're asked about. And you can get your acceleration by finding the slope of that graph. These are all lines, no curves. All right, can we go on to page 31 then? Yep.
For velocity time graph, moving with the constant velocity, could you explain like the quadrant 1 and 2?
Quadrant 1 is above the x-axis, quadrant 4 is below it. Okay. So this page, we got to turn sideways. Let's start with the column on velocity. If you have no motion, your velocity is 0. If you have a constant velocity to the right, your velocity is positive. If you have a constant velocity to the left, it's negative. If you are speeding up, moving to the right, your velocity is positive. The word right is what tells you it's positive. If you're speeding up to the left, left is what tells you the velocity is negative. If you're slowing down to the right, again, the word right means the velocity is positive. If you're slowing down to the left, the word left is what tells you your velocity is negative. All right, let's now talk about accelerations. If you're not moving, you don't have any acceleration. If you have a constant velocity to the right, you have no acceleration. If you have a constant velocity to the left, you don't accelerate. If you're speeding up as you go to the right, your acceleration is positive. If you're speeding up as you go to the left, your acceleration is negative. If you're slowing down as you go to the right, your acceleration is negative. If you're slowing down as you go to the left, your acceleration is positive. All right, let's now look at the ticker tapes. So if you're not moving, you just have a single dot on your ticker tape. If you have a constant velocity to the right, you expect to see your dots equidistant, and you're reading it from left to right. That's why the arrow is above it, showing you which way the object was moving. If you have a constant velocity to the left, it looks like the same thing, but the arrow is drawn to the left. Dots must be equidistant. If you are speeding up as you go to the right, you're going to read this from left to right, and the dots get further and further and further and further and further apart. If you're speeding up as you go to the left, you're reading this from right to left, so arrow pointing to the left, and the dots are getting further and further and further apart as you go from right to left. If you're slowing down as you go to the right, so the arrow's to the right, we see our dots getting closer and closer and closer and closer and closer. If you're slowing down as you go to the left, we read this with an arrow to the left. Reading it to the left, we see the dots getting closer and closer and closer and closer and closer. All right, let's talk about the position time graphs. If you're not moving, you expect to see that horizontal line somewhere. Doesn't matter where, any horizontal line. If you have a constant velocity to the right, this graph needs a diagonal line with a positive slope. If you have a constant velocity to the left, your position time graph is a diagonal line with a negative slope. If you're speeding up as you go to the right, you're going to see a parabola that gets steeper and goes up. If you are speeding up to the left, you want a parabola that gets steeper but goes down. If you are slowing down to the right, you need a parabola that goes up but levels off. If you are slowing down to the left, you need a parabola that goes down and levels off. All right, let's look at the velocity time graphs. Try to fold this over so it shows up on the screen a little easier. There we go. Okay, if you're not moving, your velocity time graph should be a horizontal line right on the x-axis. If you have a constant velocity to the right, it's a horizontal line up above the time axis. If you have a constant velocity to the left, it's a horizontal line below the x-axis. If you're speeding up to the right, you expect to see a diagonal line up in quadrant 1 that has a positive slope. If you are speeding up to the left, you expect to see a diagonal line, which is down in quadrant 4, that has a negative slope. If you are slowing down to the right, we expect to see a diagonal line up in quadrant 1 that approaches the x-axis, negative slope. If you're slowing down to the left, we expect to see a diagonal line down in the 4th quadrant that is approaching the time axis, positive slope. All right, so that gets us through page 31. So let's now look at page 32. What is acceleration? Define it. It's the rate of change in an object's velocity. Number 2, what kind of quantity is acceleration? It's a vector. So what do you have to include? You not only have to include the magnitude, but you also need a direction. Number 3, what's the equation for average acceleration? Acceleration is change in velocity over time, or VF minus VI over T. Number 4, the units for acceleration are either meters per second or meter per second squared. Change this out. What are 3 ways acceleration can occur? By either speeding up, slowing down, or changing direction. What is an object doing if the initial velocity and acceleration are in the same direction? It's speeding up. What is it doing if they are in opposite directions? It's slowing down. Number 8, define these. What is a constant acceleration? That's a constant rate of change in an object's velocity. What is an instantaneous acceleration? It's how an object's velocity is changing at one specific moment in time. An average acceleration is how an object's velocity changes over a period of time. For your test tomorrow, all three of these will be the same thing. We're not dealing with any kind of change in acceleration in this unit. So all three would be the exact same thing.
Like acceleration.
It's just acceleration, period. Your course is limited to accelerations that are always the same. All right, number 9, how do initial velocity and final velocity differ? Well, your initial velocity is an object's velocity before it accelerates. The final velocity is after it accelerates, or at some starting time and some ending time. And number 10, there are 6, I said 4, but change that to 6. There are 6 constant acceleration kinematics equations that you should know. They were on page 29 in the review. They are these right here. VF is VI plus AT. D is VIT plus 1/2 AT squared. VF squared is VI squared plus 2AD. A is change in V over T. V bar is D over T. And V bar is VI plus VF over 2. These are in no particular order. All right, let's now go to the multiple choice, which starts on page 34. I want to just give you the answers to all the multiple choice on pages 34, 35, 36, 37, 38, 39, 40, 41, and 42. Let me just give you the answers to all of them, and then I'll take questions on all of those pages, okay? All right. So 1 is D, 2 is D, 3 is A, 4 is B, 5 is D, 6 is A, 7 is C, 8 is D, 9 is A, 10 is B, 11 is D, 12 is D, 13 is C, 14 is C. 15 is C. 16 is A. 17 is C. 18 is B. 19 is D. 20 is D. 21 is B. 22 is A. 23 is A. 24 is B. 25 is A. 26 is A. 27 is C. 28 is B. 29 is A. Number 30 is A. 31 is A. 32 is C. 33 is C. 34 is A. 35 is B. 36 is B. 37 is A. 38 is C. 39 is D. 40 is A. All right, let's look at page 41. On page 41, 1 is 3. 2 is 4. 3 is 2. 4 is 3. 5 is 2. And on the last page, 6 is 3. 7 is 4. 8 is 2. And 9 is 4. All right, so that gives you the answers to all of those. Let's see what questions you'd like to go over on those remaining pages. Anything there, you got to give me the page number first and then the question number. Any of those questions you want to go over? Khalees? 34, number 7. All right, 34, number 7 says the graph at the right represents the motion of a cart. According to the graph, as time goes up, what happens to the speed? Okay, the speed is like velocity. Oh, it's the wrong pencil. That one keeps breaking. the speed would be found by like velocity, which is the slope. The magnitude of the velocity is our speed. So look at the slope. Look at the slope here, here, here. That steepness does not change as the time goes on, which means that the speed is constant. Remains the same. Anything else that you'd like to ask? Chaudhry?
Number 3 on page 41.
Page 41.
Sorry.
It's okay. 41, number 3. Okay, to do these, we need to use guess method. We have an object initially traveling at 20 meters per second west. When I tell you tomorrow, you will not see the word decelerates. You're going to see that it will say slows down. Slows down uniformly at 4.0 meters per second squared for 2.0 seconds. What is the displacement during those 2 seconds? All right, so first thing I need to do is remember that west is a negative direction. And when you are slowing down, that means your acceleration is opposite that. So that means in this case, our acceleration is a positive value because our initial velocity is negative 20 meters per second. The acceleration would be positive 4.0 meters per second squared, and the time is 2.0 seconds. We're looking for the displacement. So there's my givens, there's my unknown. Now what I have to do is look up an equation from page 6 of the reference table, which involves those 4 variables. And the only one that has all 4 of those is D is VIT plus 1/2 AT squared. So that's the equation I'm going to use. I'm now going to do my substitution with units. So that is negative 20 meters per second times 2.0 seconds plus 1/2 of positive 4.0 meter per second squared times 2.0 seconds squared. Now I'm going to get my answer. I'm going to do the math. Negative 20 times 2 is negative 40. Half of positive 4 is 2. 2 times 2 squared is 4. So 2 times 4 is 8. And that is a positive 8, which gives me negative 32 meters. Now, what does the negative mean? It means west. So my displacement is 32 meters to the west, which is choice number 2. Yep.
I do have a question.
Yep.
Why'd you put the acceleration as a positive?
Because anytime you slow down, your acceleration is in the opposite direction of the direction you're moving in.
Oh,
That's a pattern you need to know.
so when it slows down, it's the opposite.
Correct. Always.
So when it speeds up,
Same.
it goes.
Then it's the same. So if this was speeding up, then that acceleration would need to be negative.
What if you, I use positive 20 and then I did negative 4.
That's fine, but then you're going to get a positive answer. You defined west as positive, so you would still get west. Khalees. Number 5 on page 41. As the time required to accelerate an object from rest to a speed of 4 meters per second goes down, what happens to acceleration? So this involves a mathematical relationship here between acceleration and time. These 2 variables have what we call an inverse relationship, which means as the time goes up, the acceleration will go down. The longer it takes you to accelerate to a particular speed, the smaller your acceleration will be. This is what we call an inverse relationship. So if I were to make a graph of the acceleration versus the time, I would see a hyperbola. The correct answer is 1, yes. Anything else you would like to ask? Simi? Sure. Page 36, right? Okay. Number 19. And this question comes from this graph here at the top of the page, because this is questions 15 through 19. We're looking at a speed time graph, which is like a velocity time graph. And I'm asking you, what is the average speed between 6 and 8 seconds? There's two ways to do this, Sydney. We can either use V bar is VI plus VF over 2, or you can read the velocity at the middle time. The middle time between 6 and 8 seconds would be 7 seconds. So I'm going to do it both ways. So the first way is to get the starting velocity at 6 seconds. So if I read the graph at 6 seconds, go up and over, I see that starting velocity is 25 meters per second. The final velocity would be the velocity at 8 seconds. So I read the graph at 8, go over, and I see now that it's 10 meters per second. So we add those up and divide by 2. That gives me 35 over 2, which is 17.5 meters per second. Now, is that what I get when I read it at 7 seconds? Well, let's find out. Here's 7 seconds. We go up and we go over, and sure enough, that looks like it's about 17.5. So that's how we get choice D. You can do it either way, whichever way you prefer. Anything else? Kiara?
Same page 21 and 22.
Okay, 21 and 22, we have to read the paragraph above the graph. It tells us that we have an object that this is the velocity time graph for a 2-kilogram cart. It starts off at rest, which I can see the velocity at time 0 is 0, and then it's going northward. It starts going northward, which means these velocities here are north, and these velocities here indicate south. So let's actually look at 22 first. 22 asks us, in what direction are we moving at 4 seconds? So I go to the graph at 4 seconds, go up and over, and I see that the graph is in the north quadrant, which means I'm traveling north. That's why it's A, north. We got a positive velocity here. Positive velocity in this case means north, not east. How do we know that? Because it says it right there. Okay, it's the sign of your velocity, gives you the direction. Now, I want to know at which value of time t will we be back at the starting point? When you are back at the starting point, that means your displacement is 0. Where is your displacement 0? That means the total area between the velocity line and the time axis must add up to 0. So keep in mind your time axis is right here. Anywhere between 0 and 5 seconds, that area is positive. In order to get a 0 area, when I have positive area, I'm going to have to add a negative area to it. So that means it's got to be beyond 5 seconds. Notice that the only time given that is beyond 5 seconds is 8.5 seconds. So 8.5 seconds would be here. This would be the area up to 8.5 seconds. That area is negative. And it just so happens that this area and that area, which was all positive, are going to cancel each other out to give us an area of 0. Did you have to calculate that area to be 0? No. It's the only one that makes any sense of the choices given. The point where you are furthest away from your starting point is at 5 seconds, because that's where we get the largest positive area. After that, you started going backwards towards your starting position. That's what the negative velocities are telling us. Make sense? Okay. Khalees? Correct. And we are told that it starts off north. So this is a north-south question, not an east-west question. Yes. Number 20 is giving you a speed time graph, and I want to know the total distance traveled in the first 4 seconds. You have 2 ways you can do this. You can either look at the area, or you can use that the average velocity is the distance over the time. Either way, which means that the distance would be the average speed times the time. I'm going to do it first with the area. In the first 4 seconds, that's the area I'm looking at, which is a triangle. So that would be 1/2 of 4 seconds times 2 meters per second, which gives me 4 meters. Choice D. Make sense on that? Okay, if I did it with the distance is the average speed times the time, I would get the average speed by taking my starting speed, 0, adding it to my final speed, 2. 0 plus 2 is 2, and then dividing by 2. So it's 1. So this would be 1 meter per second times the time interval, which is 4 seconds, which gives me 4 meters. So I get the same answer either way.
Is there another way to do it?
Nope. It's either area or distance is average speed times time. Yep, same idea, except in the first 3 seconds, notice that we have 2 different shapes. So you have to do that method, either the area for each shape and add them together, or use distance as average speed times time for each time interval, because you have 2 different lines. I'm just going to do area. In the first 3 seconds, I have a triangle and I have a rectangle. So let's start with the area of the triangle. That would be 1/2 of 1 second times 10 meters per second. And then I'm going to add that to the area of the rectangle, which has a base of 2 seconds and a height of 10 meters per second. 1/2 of 1 is a half. A half times 10 is 5. 2 times 10 is 20. So that gives me 25 meters for the distance traveled. Ryder?
Number 3 on page 34.
Yeah. Okay, we have a displacement time graph, and I want the average velocity. The average velocity from 0 to 3 seconds would be the slope of the secant line, which connects those 2 points. Here's 0 seconds, here's 3 seconds. Find the slope of this line right there. So I'm going to do that by reading off the displacement from 0 to 3 seconds. That would be the rise, which is 3 meters. And the time is 3 seconds. Rise over run. 3 over 3, which is 1 meter per second. Anything else on any of those multiple choice questions at the end of the packet? Khalees? Okay, I'm asking you to compare these accelerations. Acceleration is the slope of a speed time graph or velocity time graph. Okay, notice that we're asking you to compare the acceleration of A to whatever it is with B. So A has a greater acceleration than B because it's steeper. Okay, now how much bigger is it? It's not a third, it's not the same. Is it twice as big or 3 times as big? What I'm going to do is just look at a certain time interval from 0 to 2 seconds. B is only going up 5 meters per second, where A went up 15 meters per second. 15 is 3 times the value of 5, so it went up 3 times as much in the same time, which means the acceleration is 3 times as great. Gianna.
Number 27 on page 37.
Yep. All right, which object travels the greatest distance? And we have these 4 speed time graphs to look at. Distance is the area. I don't actually have to calculate areas. What I'm going to do is shade them in, and I'm going to look for the biggest shaded shape. There's one. There's another. There's another one. And there's another one. Which one is the biggest shape? Say. So you don't have to do any calculation. It's a visual question. If you understand the pattern that on a speed time graph, you get distance by looking at the area, you just shade them in. Which one gives you the biggest shape? You could calculate them all, but that's an awful lot of work. And you probably don't have time on a test tomorrow to do that for all 4 graphs.
Is it 1 period?
Yep, tests are always 1 period. Anything else? Khalees? 23? Same thing. Which one is traveling the greatest distance from 10 to 16 seconds? Now, we're not showing you the horizontal axis. These are speed time graphs. So the 0 axis is down here. So I'm just going to shade in what I can. And whichever one gives me the biggest shaded area between 10 and 16 seconds has the greatest distance, because this is a speed time graph. So I can tell you right now it's A, because look at where A is. It's the highest one up. So I'm going to start with D. Here's 16 seconds. The area for D is that section right there. See if I have some colored pencils to do the others, or pens. The area for C would be this triangle. And you see that's bigger than that curved area? Okay. Let's now see. Do I have another color? Yeah, purple. Okay, if I do it for car B is here, which means I would shade in all the way down. That's even bigger than those. That gives me a bigger rectangle. And if I do it for car A, here's car A, I would have to shade that in all the way down. You see how car A gives me the biggest area? Therefore, it's the biggest distance. Anything else you want to ask on the multiple choice? All right, I'm going to just make an executive decision. I will stay after school today, but I will leave at 2:45. Okay, if no one's here at 2:15, I'm leaving. So if you want help, be here by 2:15. I'll give you a half hour to ask more questions, and then that's it. This way I don't have to worry about trying to hop on a Google Meet later today. Okay? Please make sure you have pen, pencil, ruler, calculator for tomorrow's test.